Okay, yeah. Well, thanks very much for the invitation to speak and for the organizers for organizing this this excellent session today. Okay, so yeah, so many fundamental problems in robotics and AI can naturally be formulated as making the best possible decision under a given set of circumstances. Things like learning, perception, state estimation very naturally fit into this formulation. And so most of these problems, as you know, can be very naturally formalized using the language of optimization. And if you read a lot of papers in the literature, this is roughly the way that these problems will be expressed. So why can't we just take those problem formulations, plug them into our favorite optimizers, and just be done with it? Well, unfortunately, it turns out that most of these problems that we want to solve turn out to be both high dimensional and non-convex, right? And of course, that's just because oftentimes we have a lot of parameters that we want to estimate, and a lot of the constraint sets that turn out to involve many of the states that we want to estimate, things like orientations, for example, and pose estimation, are non-convex sets. And so, anytime you see things that are both non-convex and high dimensional, that should be setting off alarm bells, because those problems are almost always difficult to solve in the sense of computational complexity theory. And so the way that ends up showing up in applications is through the appearance of lots and lots of bad local minima in the loss landscape for the function that you're trying to minimize. So one sort of motivating example that has inspired a lot of the work that my group has been thinking about over the last several years is this problem of pose graph optimization. And for those of you who haven't seen this before, I know Luca mentioned this earlier today at the start of his talk, but the basic idea is that you should really think of this as being the mathematical abstraction of robotic mapping and navigation problems. So the basic idea here is we're given a collection of unknown poses, that is robot orientations and positions that we want to estimate. And we have some way of measuring what you can think of as being noisy pairwise relative motions between these unknown poses. And so, these operationally are things that come from things like odometry measurements, like IMU integration or wheel encoding, or things like laser scan matching. And so the idea then is, we're given these noisy relative motion measurements, and we want to estimate then the trajectory the robot has moved through that best agrees with these motion estimates. Okay, so under some reasonable noise model, you get some high dimensional nonlinear optimization problem that looks like this, and the punchline is this is one particular example of what one of these problems might look like. And this is high dimensional because there's typically just a lot of poses that you need to estimate, and it's of course non-convex in part because the orientation states that you have to estimate are themselves members of a non-convex set. Okay, so you might say, Dave, okay, well, people solve non-convex optimization problems all the time in deep learning, so is non-convexity really a major obstacle here? And what I want to show you here is that it turns out the answer to that is yes. And so here what I'm showing you is an actual data set that was collected by the Stanford autonomous car, where this thing is driving through this parking garage. And what I'm showing you here is the actual real globally optimal solution for this particular trajectory estimate for this problem. And you can see, you can pick out the parking ramps inside the structure pretty nicely. Now, if I were to do sort of the usual thing that you might think, where I just pick some random starting point and I try to go downhill using some off-the-shelf technique like gradient descent, what are the kinds of things that I might get? Well, I might get things that look like this. So this is, again, an actual suboptimal critical point for one of these robotic mapping and navigation problems that is gotten in exactly that way. And so, what I hope I've convinced you of in this sort of brief introduction is that these questions of safety and reliability, when we're trying to do inference or planning or control using local search applied to non-convex problems like this, is actually a big deal from the standpoint of like safety and reliability when we're using these techniques to control safety critical systems. And so a lot of the work that my group has been doing over the last few years and with collaborators has been asking, whether or not it's possible to develop optimization techniques that are fast and scalable enough to be applicable to real-time robotics applications with lightweight compute and lightweight hardware, but that also enable you to say something stronger about the quality of the solutions that you can get in tractable time for this very difficult class of optimization techniques. And so what I wanted to just briefly touch on in this talk was just to introduce two recent lines of work along these lines that are aiming to develop fast, scalable, and provably sound optimization techniques that are really targeted towards the operational constraints of robotics problems. So in particular, I'm going to tell you a little bit about this class of techniques that Luca mentioned this morning, these certifiable optimization methods, and then also how we can also think about designing distributed optimization techniques for multi-agent systems. Okay, so just to recap, for those of you who may not have seen Luca's very nice talk this morning, the main sort of difficulty in the design of these techniques is the fact that all the problems that we want to work, or almost all the problems we want to work on, are non-convex. And so, as I mentioned before, the fundamental problem here is that because of these computational complexity theoretic reasons, you shouldn't expect to be able to efficiently solve general NP-hard, non-convex optimization problems in general. But if I stop and think for a second about what that actually means, the notion of NP hardness is a worst case adversarial notion. All that means is that, if I give you some problem class and you give me some algorithm that you claim can solve every example of one of those problems, I can go into that example. I can go into this problem class and I can pick out, one or a handful of instances of that problem that make your algorithm have to work super hard. But that doesn't say anything about how prevalent those very difficult cases are. And so, thinking about this from sort of an intuitive standpoint, what you might hope is that the actual picture, if I were to have a slightly more refined picture, that more refined picture might look like this, where I've got, some collection of cases that are really hard, but perhaps optimistically, if I don't think that nature is actively out to get me, I might hope that the set of problems that actually show up in real world applications, that is the actual problems that I get when I have real data coming off my sensors, are perhaps in some sense a little bit easier to solve than these worst case instances that make this overall problem class very difficult. So maybe what I could think about doing then is well approximated in some sense reasonable instances of these problems. Okay, so that's a nice idea, but how would I operationally do that? Yeah, how do I operationally, actually do that in practice? So one general approach that my group has been getting a lot of mileage out of over the past few years is to use this idea of convex relaxation. So the idea then is what we're going to do is we're going to start by taking one of these difficult non-convex problems. We're going to produce a convex approximation of it, and we're going to solve that surrogate instead. And the main advantages to doing this are that there's nice standard ways of constructing these relaxations for fairly broad classes of problems, things like outer approximation and Lagrangian duality and so on. And because it's a lot easier to analyze convex problems than non-convex ones, it turns out that you can actually, in certain cases, be able to actually provide performance guarantees for these convex approximations in terms of how good those estimates are going to be. Okay, so I thought I might briefly show you exactly how this can be done for the class of polynomial optimization problems. So as Luca mentioned, this seems to be a sweet spot between generality and tractability. So this is an assumption that will give you global control because you're only a polynomial if you're a polynomial everywhere. But this is rich enough that it allows for non-convex problems. And so it's quite a bit more flexible than the usual assumption of convexity that you might typically use to get global control over some of these problems. So we're going to assume that we're given an instance of a polynomial optimization problem that we want to solve. So that is an optimization problem in which the objective constraints are polynomial functions. And what I'm going to show you here is how you can take that and produce a convex relaxation from it in a purely mechanical way. So the first observation is, it's always possible to take one of these pops and rewrite it specifically as a quadratic optimization problem. And the main idea here is this actually is relatively straightforward. All you have to do is just realize that if I have any monomial term that appears in that problem that has a power greater than 2, all I have to do is just introduce some auxiliary variables. If I see something, if I see a quadratic expression like this, I can just introduce a new variable that I will just define to be equal to that. So that introduces a new variable, it introduces a new constraint, but the effect is I can now replace this quadratic term with a linear term, and that reduces the power of that term by 1. And if I just iterate that procedure, I can eventually get down to having an optimization problem that it has at most powers of 2 and is therefore quadratic. So, and then of course, once I do that, there's a totally standard way of generating semi-definite relaxations of quadratic optimization problems, which is just to observe that if I have a QCQP that looks like this, I can simply replace this rank 1 outer product, which is positive semi-definite by construction, but also for rank 1, with just a generic positive semi-definite PSD matrix of an arbitrary rank. And what that gives me then is an immediate convex relaxation of this that is a minimization of a linear objective subject to linear inequalities, equalities and inequalities over the positive semi-definite cone. So the punchline, or one of the, why is this an advantageous thing to be able to do? Well, this gives me really two sort of major advantages. So the first is that because this is a relaxation of my original problem, the optimal value of this problem, whatever it is, gives me a lower bound on the optimal value of the problem that I start with, which allows me to measure how well I'm doing for a given, if I have an estimate for this problem, I can compare that. I can use basically this lower bound as a way of determining globally how well a given candidate solution to this problem is. The second thing that is perhaps more interesting is, if I solve this relaxation and it turns out that the solution that I get is actually rank 1, so it factors in this way, it's easy to show that this low rank factor actually globally solves my original problem, exactly because if I plug this in, it attains this lower bound on the optimal value for my original problem. And so the punchline then basically is, so that's great, but like, why would, maybe that's not immediately obvious why this is interesting. One of the main reasons that we're actually interested in this particular relaxation strategy is that it often turns out in application that this favorable situation actually occurs in applications. That is, for many of the problems that we care about, it does turn out that we get a solution that looks like this. And the implication then is that gives us actually a way of solving these very difficult non-convex optimization problems by means of solving an associated convex relaxation. So just as one particular application of this, one of the first papers that we worked on when we were sort of thinking about these techniques was to apply this to postgraph optimization. And actually in that particular problem, which is this very fundamental estimation problem in robotic navigation, we were actually able to show that not only does this often occur empirically, but in fact we can prove that it will occur. So in fact, one of the results we've been able to prove in this case is that if the noise that's on the measurements falls below a certain critical threshold, then in fact, this STP relaxation that we can produce in the way that I just described does in fact have a unique solution. And that unique solution factors in exactly the way that we need in order to recover a global minimizer of our original problem. And so the punchline then basically is what this is really saying is this actually is guaranteeing that under reasonable conditions, this approach will actually work. It will give you a way of recovering these globally optimal solutions. Okay, so that's great then, right? So we've got a nice relaxation procedure. We've got some reason to believe this is actually going to give us the right answers. So now all we have to do is just solve the corresponding STP. So am I doing on time? Yeah. Okay. So if I just pick some off-the-shelf STP method, I can, like Sadumi, for instance, I can imagine just plugging in that corresponding semi-definite program and just seeing, seeing whether or not it works, right? And unfortunately, it turns out that this direct approach doesn't actually work all that well. And it's not too hard to see why. The cost that I have paid for constructing this relaxation is that I've essentially blown up the state that I'm trying to estimate from an n-dimensional vector to an n-by-n dimensional matrix. And that's just a much, much larger object. It's much heavier duty. And as a result, it's these off-the-shelf techniques don't actually scale all that well. So to get a sense of scale, I'm showing you here a simulation involving only a small synthetic example with only a couple hundred poses. And what you can see is that solving this problem is taking on the order of about 20 minutes. So to give a sense of scale, we would need to solve problems that are 1 to 2 orders of magnitude larger than this, in order of magnitude, let's say seconds, in order for this to be practically competitive with existing local search techniques. On the other hand, these are totally generic methods that will solve any STP. And so we might, kind of thinking back to our proposal or our previous slide, have the idea that, well, maybe I don't want to solve every STP. Maybe I can build specialized techniques that are really well suited to these particular classes of relaxations. And so the technique that we've been sort of using to solve a lot of these in practice efficiently is and the basic idea is what that theorem that I showed you earlier guarantees is that for this particular class of relaxations, we expect that many of these STPs relaxations are going to have low rank solutions. And so there was a beautiful idea proposed by Biral Montero a few years ago the basic idea is, if you know that you're trying to solve an STP that should have a low rank solution, rather than doing direct optimization over this large matrix Z, you can simply hypothesize that it has a low rank symmetric factorization, let's say rank R, and directly substitute this factorization into your original STP in place of Z. And if you do that, what you will get then is a problem in which your decision variable, of course, is now much lower dimensional than Z itself, so it's easier to work with. And it's not too hard to see that as long as you pick this rank sufficiently large, that is greater than the rank of some solution to your original problem, then the any global minimizer Y star for this symmetric factored program is going to give you a low rank factor for a solution of your original STP. Okay, so the punchline then basically is what this gives you is it gives you a way of efficiently searching for solutions of these low rank STPs by means of just doing low rank nonlinear programming of the sort that you ordinarily would. Okay, now, if you guys have been sort of following some of this so far, you might be asking a question because, we started by saying we're going to solve these non-convex QCQPs. We produce these STP relaxations, which were nicely convex. But then we said these are too hard, and so now we're going to do this factorization. And so you might say, okay, well, it seems like we've kind of gone in a giant circle here. So what is the actual benefit to doing this? The actual benefit is that we've given ourselves a little bit more room to work with because we're not requiring that these factors are rank 1. And it turns out that little bit of extra room is actually enough to guarantee that we can recover globally optimal solutions. And so in order to see that, it's actually helpful, I think, to look at the first order KKT conditions for this pair of problems. And so if I sort of put these things side by side and stare at them, what I might notice is that the only way in which these differ is that this certificate matrix, which appears in both of these KKT conditions, is required to be positive semi-definite for the STP problem that I started with, but not necessarily on the right. And so the implication of that is if I solve this problem and I declare that I'm going to take Z as a guess for my STP solution, I can simply then evaluate whether or not this certificate matrix that I construct from my NLP solution is in fact PSD. And if that is the case, because this problem is convex and therefore these conditions are both necessary and sufficient, I know that this STP matrix actually is a solution to my STP. So that is to say, this gives me a way of easily verifying the global optimality of a candidate solution that I've gotten by means of solving these low-dimensional non-convex programs. And in fact, you can actually go the other way as well. So one of the things that one sort of result that we've proven recently is not only does this work for verification, but in the event I try that, so I locally solve my low rank program, I get a low rank factor, and I test whether or not that's a global minimizer. If that test fails, that test failed because this matrix is not PSD, and if it's not PSD, it has a direction of descent. It has a direction of negative curvature. It turns out you can additionally show that if I have one of those directions of curvature, that actually gives me a descent direction for another instance of this low-rank nonlinear program that is of rank 1 dimension higher. And so this gives me a kind of a nice theorem of the alternative then, where essentially what I can do is I can turn this into an algorithm, an optimization algorithm for semi-definite programming by means of doing these low-rank searches. And the idea basically is it's actually fairly straightforward. All I'm going to do is I'm going to start with an initial guess for a solution to my problem. And I'm just going to locally do optimization on these low-dimensional NLPs. And when I get my stationary point for this low-dimensional NLP, I'm going to check whether or not this matrix is PSD. If it is, then I'm done. And if it's not, all I'm going to do is I'm just going to increase the rank of this by 1. That theorem guarantees that this is going to have second-order descent direction. And so as long as I'm using second-order optimization here, that will allow me to continue optimization at the next highest instance of this relaxation, or this low-rank factorization. So the punchline basically is what this algorithm is really describing is a way of applying the same kinds of low-dimensional nonlinear programs that we're already using in things like GTSAM and so on, but actually wrapping these in a very lightweight outer loop that allows me to guarantee recovery of globally optimal solutions by means of these very fast low-dimensional optimizations that look almost identical to what we would ordinarily do. Okay, I think in the interest of time, I'm going to go through this fairly quickly. So this is basically showing, this applied to some large-scale SLAM benchmarks. And the punchline here I just want to point out is, number one, these things are in fact finding globally optimal solutions for real-world problems. So these things do actually work as the theory would suggest. We can do this for actually quite large STP instances now. So these are, things involving tens of thousands of poses. So these are STP relaxations that are on the order of 60,000 dimensions, let's say. So quite large STPs for those of you who may not have worked with these intimately before. And we can do this on lightweight robotic hardware, single-threaded in a matter in time that is competitive or useful for real-time robotics applications with lightweight hardware. So these are in fact practically useful techniques. Okay, I'm going to maybe skip over this in the interest of time. Yeah, so the main takeaway that I want to leave you with here is basically that these STP relaxations provide actually quite a powerful approach for building optimization techniques that are both fast, globally optimal, but that also can preserve the speed of existing state-of-the-art techniques. How much time do I have left? 5 minutes? Okay, perfect, great. Okay, so really what the Senate is saying is, we have a way that we can now do, tractable, fast, global optimization, but everything I've described so far has been really, you can think of it as being a centralized algorithm. And so if I want to think about really pushing the scalability of these techniques, I might at some point need to be...
recently we made it.
Okay. Yeah, at some point, I might want to think about trying to scale these problems that require more than a single agent. So a good example of this would be something like, very, very large scale mapping of the sort that I might do with teams of drones or autonomous vehicles, where there's just so much ground to cover that I really need more than one robot. And so at that point, if I'm thinking about having multi-agent systems where I have different agents that are collecting different measurements locally, there is some, let's say factor graph model that might describe that total problem. But the data is not centrally located, right? Different agents have access to different measurements. They're aware of different things in the environment and so on. And so, I really want to think about probably solving this in a distributed fashion where I don't have to do a lot of data movement and so on. And so, certainly we're not the people to think about distributed optimization. This has been well studied in the machine learning literature since the 80s. But almost all of the common distributed optimization techniques that you would come across if you look through the literature, things like consensus ADMM and so on, start with the assumption that the problem you are trying to solve is a convex problem. And as we said before, there are very few interesting robotics problems that are truly convex. And so the punchline basically is that a lot of the standard optimization techniques that one would use just don't apply to distributed robotics problems. And so there hasn't really been what I would say is a general purpose distributed optimization technique that is really adapted to the requirements of robotics applications. So quick one slide summary then. One of the other things that we've been thinking about recently is actually showing that you can use Riemannian geometry or ideas from some of the Riemannian geometric ideas that Noemi mentioned earlier today to develop distributed optimization algorithms that admit actually both non-convex objectives and constraints. And the key insight that underpins our approach to this is just the observation that a lot of these optimization problems that arise in these robotic applications satisfy two key properties. So the first is that the feasible set, although non-convex, is a product of smooth Riemannian manifolds. So that's observation number one. And observation number two is that the objectives also often tend to be a sum of functions that individually only depend upon a relatively small number of variables. And so, I saw Frank earlier today. In fact, if you look at these for a second, what you might recognize is that these are exactly the same hypotheses that underpin the design of factor graph models. So the same problems that you can model with a factor graph are basically the ones that satisfy these two assumptions. And so, these are quite common. Okay, so what are the implications of this then? These observations are useful because what it means is that we are actually in the very special case where we can actually guarantee that non-convex constraints are always exactly enforced. And that's because we know the actual geometry of these underlying smooth manifolds. And so we don't have to worry about constraint satisfaction in these cases. That's observation number one. And observation number two is that because we don't have to worry about constraint satisfaction, these problems look like unconstrained optimization problems. They're unconstrained optimization over smooth manifolds. And so the punchline then is that because they are unconstrained optimization, all we have to do is just at each iteration, if we can enforce a reduction in the objective value, that is actually enough to guarantee the convergence of a distributed optimization method, even in the non-convex case. So based on this insight, some of my collaborators and I, this is joint work with Yulin Tian and Kadri Kasusi, have proposed this block coordinate Riemannian descent method, which does sort of general purpose distributed optimization over Riemannian manifolds. And the basic idea is very straightforward. All we do is we take our variable set that we want to optimize over, and we partition this into case subsets that we can think of variables that we can think of as being in one-to-one correspondence with the agents that we are going to be collaborating to solve this problem. So each agent is responsible for optimizing a certain subset of variables. And the algorithm is very simple. All we do is at each iteration, we pick a block of variables that we want to update. We calculate a single trust region update step, which is designed to improve this function value by minimizing one of these subblocks. Agent K is going to update that variable block using a retraction. And any variables that it needs to, that are shared or neighbor a neighboring partition, it's just going to transmit to its neighbors. So basically, each iteration of this basically just consists of computing one update, a single update step that improves the objective by manipulating one subblock of variables. And it's easy to see that by construction, because this is just constructed as sequential partial minimizations, this is going to generate a sequence of updates that monotonically decrease the objective. And that actually is enough to prove that this method will converge to stationary points in exactly the same way that centralized gradient descent does. And so the punchline is actually what this method gives us. Basically, the punchline is this establishes there's actually zero gap between what we can do in the centralized and the decentralized setting now in terms of functions that we can actually optimize. So anything that you could do with a centralized factor graph optimization technique like GTSAM can actually be solved in a decentralized fashion using this distributed approach. So I think in the interest of time, I might wrap up here, except to say that we've actually applied this to certifiable distributed robotic mapping. And for those of you who have seen the Chimera multisystem, which is a beautiful piece of work on multi-agent mapping from the Spark Lab, This is actually the algorithm that is running the optimization technique that is being used under the hood in Chimera Multi. So those of you who maybe have experimented with that technique before, you were in fact using this work. So yeah, I know this is sort of like a lightning overview to sort of different ways of thinking about non-convexity. But the main thing I would point out here is just this sort of a very exciting emerging area, how to handle non-convexity and robotics problems in a principled and an efficient way. There's lots of interesting stuff to do that remains to be done. And for those of you who like this kind of thing, I would just mention that my group is always looking for students, collaborators, and so on. So please do send me an email if this seems like the sort of thing that you might be interested in continuing to push on. And thanks.
Thank you, David. We can maybe take one question.
Hi, thank you for a great talk. So I was wondering on your work on low-rank semi-definite programming. When you go to using a local nonlinear optimization method, how sensitive is this to your initial guess, and how do you obtain the initial guess? Thank you.
Thanks. So certainly the local optimizations are the solutions that you get from each local optimization is certainly going to depend on where you start. So in that sense, they're sensitive in exactly the way that you would ordinarily expect. The significance of this theorem and this resulting optimization method is basically has to do with, suppose that I do my local optimization and it turns out that the solution that I get is not globally optimal, which I can check directly just by looking at the KKT conditions. What this second part of this theorem indicates is that if I do this check and it turns out that my local optimizer did not produce a globally optimal solution, what this descent direction gives me is it gives me a second order direction of descent from that stationary point that will allow me to continue local optimization while still monotonically decreasing the objective. So what I can do then is basically I can wrap these local optimization methods in an outer loop where even if each individual local optimization technique doesn't quite get me to the finish, I can still continue the search in a way that will eventually get me there through a sequence of local optimization. Does that make sense? Okay. Oh, you can just pick whatever you want, and the advantage to that is that exactly because this no longer I don't need to get to the correct solution on the first try. I can do a sequence of them, and so the purpose of this basically is to show that I'm no longer dependent upon a good initial guess to get to the globally optimal solution. Sure. Yeah.
Thank you, David. Again, I think we now need to move to the next speaker. It's our next speaker is Francesco Biral from University of Trento. He's an associate professor in the Department of Industrial Engineering, and today he will talk to us about connections between direct and indirect methods for numerical optimal control. And we are very excited to hear this talk.
Okay, so I'm proud to be here, and I'm going to present this work, which is not only something that I did alone, of course. It has been done mainly for the numerical part of what I'm going to present here by a colleague of mine who is not here. We have been working, okay, it doesn't, sorry, I don't know why. Okay, we have been working on optimal control, starting from minimum time maneuvers, lap time maneuvers for motorcycles more than 20 years ago. And then we slightly moved to developing advanced driving assistance systems. And finally, recently we are working on autonomous driving and mainly racing driving. Even if, as you see here, we have combined not only optimal control, but with other technique for planning parking maneuver in a complex environment, or as you can see up there, racing with other opponents. Of course, there, it is not only optimal control. We need something more to plan in complex environment. And also, we need to take into account the complexity of the vehicle dynamics. What is challenging for what concerns us is that we want to maintain the non-linearity and complexity of the vehicle dynamics. And also, typically, we wanted to plan quite long range, because if you're driving very fast, for example, 300 kilometers per hour, your planning horizon has to be as long as possible to include the braking point. Otherwise, you will fail to take the corner. So it means that you need to plan more than 300, typically 300 meters or more. Another complexity that we faced was we were tackling the problem of optimal pacing for cycling time trials. Typically, the race is between 20 kilometers to up to 50 kilometers. And we want to solve the basically the optimal solution in order to distribute the effort for the cyclist. Typically, they are uphill and downhill situation, and the racer, the cyclist, has not to completely exhaust his energies. In this case, of course, the problem is quite big. You have almost 2 or 3 million optimization parameters, and we want to be quite fast in solving this. So I'm talking about minutes. So okay. In general, the optimal control problem, you will see later other talk about this. We formulate in this general way, which is what we called Bolza, we have a Bolza target, so a target on the initial or final objective, and then we have a running cost. We have, in this case, I just here reported the dynamics, explicit dynamics. Later, I will generalize a little bit. Initial and boundary conditions. Then we have inequalities, general inequalities on state and control. We have also parameters. P is the vector of parameters, and the controls are bounded, not like box, but so I mean the boundaries can be moving. And if we want to solve this problem, as you probably know, there are, let's say, 3 big family of, let's say, method. But I will talk about 2. One of this method, which is probably the most popular one. If you look at the literature, you will see that I would say 90% will be what it is called like a direct method, which means that we direct, which is quite straightforward. We take the continuous time optimal control definition. We find, we look for an approximation. So we discretize the problem and we get an NLP. And when we are there, we have, of course, different way to solve the problem. But if you want to go fast, gradient-based method are of course perform faster. And you can, if you choose this path, you can define the KKT conditions using the Lagrange multipliers. And so we have that set of equation to be solved. And it's quite popular with collocation and the use of interior point solver. Today, there are a lot of quite efficient solver and method to find this the solution. But there is another path which is based on it is called indirect method, which is the variational approach. It's based on the variational approach. So we use again the Lagrange multipliers to dualize, like in the other case, the problem. And using the Pontryagin minimum principle, we arrive to this set of equation where we have some differential equations. The original set of equations, the first line. The second are the co-equation, are called co-equations, which resemble the equation we have on the other side, actually, as I will highlight more later. And then there is another part, the last part, which is where the Pontryagin minimum principle come in, which is telling us that we can solve the controls in order to minimize locally, time by time, the Hamiltonian, assuming that the state and Lagrange multipliers are fixed. And if we do this, then we have the control history that we can basically substitute into the previous equation. So the control will disappear because they are function of the state and Lagrange multipliers. And we have a two-point boundary value problem that we can solve. The nice part here is that you can use this tool also to find analytical solutions. And there are a lot of works in this sense. But for large problems, of course, you need to solve it numerically. And when you want to solve it numerically, again, you have to choose a discretization. And you will arrive to this problem, which is a nonlinear problem, a nonlinear system, F and G, as you see there, with the same state and Lagrange multiplier. I will say same between quotes, because I will, actually, they are not. And then there is the optimization problem coming from the Pontryagin minimum principle. So essentially, we have a nonlinear system plus optimization. If we solve the optimization, let's say node by node, then we have the nonlinear system to solve. On the other side, so they look pretty similar. Actually, the point is that they are not the same, as was highlighted by the work by Ross and Farou. Actually, they said that dualization, discretization are not commutative. So if you do first dualization, then discretization, or vice versa, you don't get, even if you use exactly the same approximation, you don't get the same result. So the work done by Farou and Michael Ross was actually to, they proved that if you use what they called covector mapping principle, so it is possible to find a mapping between the Lagrange multipliers of the direct method with the indirect ones. So the idea is, okay, I solve the problem using direct method, then I have the Lagrange multiplier of the direct method. I found a mapping in order that I get the Lagrange multipliers of which actually are the co-state. So they have also a different physical meaning of the optimal control. And they say, okay, I can, at that point, I can use this information to check the necessary condition of the Pontryagin minimum principle. Okay, this is nice. And it was proved that with some Runge-Kutta discretization and pseudospectral discretization, it is possible to find this mapping. What we actually wanted to do, it is to work on the other side, because historically we developed let's say, software to generate the equation and solve the equation using the indirect method. And we wanted to, why? So we want to establish this link, because we solve actually a nonlinear system. On the other side, you solve with an optimization problem for the controls. On the other side, you solve basically an optimization problem, which has some properties of robustness, which are difficult to include in the nonlinear system. Even if we develop a really efficient and fast nonlinear system, then when we are close to the solution, let's say 10 minus 7, we cannot guarantee that we are at the solution because it's a nonlinear system. Okay, so it's quite difficult to guarantee something using the nonlinear system. So the idea is, okay, can we find a discretization in order that the two systems are exactly the same? And if we can do this on this side, then we can inherit characteristic or features technique from the solution of the minimization, the NLP, let's say, to the indirect method. This is the core idea. So I will show in the next slides how we did this and what was the, let's say, the trick. So I will first move on the lower part, so indirect method. We actually here, I use the implicit dynamics, not the explicit one, which is, and the reason is because the implicit dynamics is quite common when you have large problem and is not easy to express in implicit form. Then what we did was to use the penalty or barriers to approximate the constraint equations, both for states and controls. And these give us some properties. Of course, we are approximating the reality, but then in the solution strategy, using homotopy, you can convert, or let's say approximate as much as possible the the original solution. If you apply the first variation, so first of all, we define the Hamiltonian. So we use the Lagrange multipliers. So mu are the Lagrange multipliers associated to the dynamics. Omega, the Lagrange multipliers for the boundary conditions. And then applying the first variation, we get the equations that we have seen also in the chart, and which correspond to the original system, to the adjoint equations, both for the states and the boundaries. And we have the equation for parameters, for constant parameters, in order that we can do also optimizations. And finally, the gradient of the Hamiltonian for the optimal control. That the last part is the Pontryagin minimum principle. So this is in the continuous, and we can pose some. We can actually discuss some of the features of this formulation. For example, for some multi-body formulation, you can write the implicit form like a matrix, which is function of x and p multiplied by v, which is the derivative of the state. And if it is not singular, actually, you can exploit this during the solution of the system. And additionally, using this, we can also prove that if the second derivative of the Hamiltonian is strict positive definite, then we can guarantee the local optimality of the solution that we find. And using the penalty and barrier, actually, this is proved true. So if you take the gradient, we just used a very simple mid-rule finite difference approximation, a second order. And what we get is this. I will come back later. It's maybe this looks scary, but I will discuss later piece by piece. So in the first part is the discretization of the dynamics. Then we have the adjoints again, and the constant parameters, boundary condition, and path constraints discretized according to this mid-rule point discretization. Now, let's apply exactly the same discretization to the direct method. So, and we can do this in two different ways. One way is the first one, where that I called mode actually B, where I use exactly the finite discretization, which is the average between xk and xk plus 1, which are the stated two nodes, is the average between the two nodes. And the other one is actually a pure, so I substitute in the equation, so we substitute in the equation sk plus 1/2. It means we use, okay, we use this this substitution, which is formally identical, but not during convergence. Okay, so they are different during convergence, but when the solution will come to the end, they will be identical, but during convergence they are not. So we have these two different. This is the standard way you will do it. This is different, and the gradient, so the Jacobian, will be different. So here we just get the discretized optimal control problem, where there is the star in the Hamiltonian. It means we can substitute either this discretization or this discretization. And so we derive both of them. They are, and I will discuss now. So this is the general view of the discretization. They looks almost, so if I go back and forth, you will see they more or less are look similar, but let's look piece by piece. So what is the difference between them? So if we look at the original system, so on the top here, we have the original ODE in continuous time, the indirect method. So mode A and mode B, they are exactly the same with this discretization. So we can go to the adjoint equation. Sorry, this is the control part. So for the control part, again, they look exactly the same. So we maintain the same properties. It means that if we solve the direct and the indirect, they look exactly the same for this part. When we arrive to the adjoint equation, this is for the boundaries. And so the first line here, up here, is for the boundaries. And the second is for the internal nodes. We see that they are different. So this is what we get from the indirect method. This is with mode A and with mode B. So this part should be lambda n in order to be the same. And here, this should be 0, and this should be lambda n. So it looks like they are different. So the discretization, even if we apply exactly the same discretization to the two problems, we don't get the same system. In order to make it equal, we just introduce a new state, lambda n, which will be added and subtracted in the same, in this equation, so in mode A. So what we do is we add and subtract, and then we say that this lambda n is equal to this. So if we do this and we collect, actually we have an additional equation in the direct method. We have an additional equation which add the missing Lagrange multiplier, because if you count the number of Lagrange multipliers, you will see that for the indirect method, being a state, we have a number of Lagrange multiplier which is equal to the number of state. In the case of direct method, instead, you have -1. There is a missing Lagrange multiplier, and we get the Lagrange multiplier from this equation. So if with this approach, essentially, we have that the indirect method equation is this. With the direct method is this. Is just a scale by let's say, the size of the interval, which is positive. You can eliminate, but these two are exactly the same. With mode B, instead, which is the standard way of discretizing. Remember, mode B was xk plus 1 divided by 2. We don't get this mapping. So it means that if you go straight, as you will do, because it's the more natural way of discretizing, you don't get the same result. once we have this, we have some benefit because so we can learn. So we have learned something. If we use mode B, I remember mode B is the standard mid rule discretization with the average of the value of the state between the two nodes. We are not able to have the same system in the discretized system in the two cases. So it means that the gradient and Jacobian will be different. Instead, so it means also that the Lagrange multiplier of the direct method are not correlated to the co-state of the indirect. If we use the mode A instead, we are able to establish this link between the two. And it means that the gradient is the same. And it means that if we find a solution with one method, it will be the same solution using the other method. So if we solve the nonlinear system with the optimization of the control, sub-optimization of the control, we get a solution which is exactly the same if we use, for example, the direct method with interior point. But this also, so the benefit that we see is that it is possible now to use a technique, for example, like proximal approach into the solution of the nonlinear system. And we realize that this makes the convergence much more robust and faster for the nonlinear system. I just want also to point out that there is also a different on the system that we have to solve. For the direct method, is the band is larger, and instead for our solver we have let's say let's say a narrow band with this shape, and we developed, actually my colleague developed this fast solver for the algebra for solving this problem. So very quickly, I will come to the final solution. We do some other tricks. So we realized that looking at this expression that we can subsolve some part, not only the control, but also we can remove the vector V and the Lagrange multiplier mu, and we get a more compact system. So in the end, what we do is we solve this compact system because exploiting the minimum point origin principle, we subsolve the controls, and we treat essentially the Lagrange multiplier mu in a very similar way. This means that the system is more compact and we can reach very fast convergence. So I just like to conclude with this sentence by John Betts, where he actually surveyed the different numerical methods for trajectory optimization. And we actually like it because it's what actually we were pointing at, to try to merge the two worlds and find the best advantages of the two methods and produce a new one, which is inheriting the advantages of the other. And in this part, we are developing a new, let's say, nonlinear system, new ways to solve the optimization problem, including, for example, using ordinary differential equations. Okay, I just want to thanks also the other person working, Enrico Bertolazzi, who is the main developer of the numerical methods and the formulation, and all the PhD students that helped us in developing all the applications in the automotive field. Thanks.
Thank you very much, Francesco. I think we have time for one quick question.
I have a basic question. Like, you have this indirect method and indirect method. Does one produce better solution than the other? Does one method will produce better solution than the other? No, that's what my follow. Yeah, because all these are solving some complex nonlinear optimization anyway. So you don't get the actual solution anyway. So what is the point of making both the methods converge? What do we gain out of that?
So we have 5 minute breaks now, if you want. Okay. Okay, ready?
We will start at 11:50.
Okay, so we will start again, please. Okay, so hello everybody, I'm Justin. It's my pleasure today to introduce Russ Tedrake. So Russ is a professor at MIT, so I don't think that we need to introduce Russ, but at least a bit. So he's also vice president of robotics research at Toyota Research Institute. And today we'll talk about graph of convex text for robotics and beyond, I guess. And so thank you, Russ.
Justin. Okay, thanks everybody. Even in the last 10 minutes, I've found some people have heard a little bit about graphs of convex sets before. Some of you haven't at all, so I can't assume either way. But even if you've seen a bit about this before, I'm going to emphasize different aspects of it today. I think I've always talked about graphs of convex sets in the lens of motion planning. I'll mention that, but I want you to hear the bigger view of GCS today. So let me try. Boop, boop. Okay. Let's just take a generic optimal control problem. Okay, I've got like the ones we've been hearing about in the last talk and other things. Okay, typically nonlinear objective, nonlinear constraint. I often say in class, for instance, that there are basically two cases that we completely understand. We understand how to do nonlinear optimization, but to have strong guarantees, right? We completely understand the case where things are perfectly discrete. Everything's a Markov decision process. We have discrete states, discrete actions, discrete time. We know how to solve that completely. And we know how to solve it when it's linear and convex. So we can do LQR or linear MPC. We understand that fairly well completely. And then it drops off. The results require very special cases, but these are somehow the bedrock. And I always try to make sure what I'm thinking about sort of works for one of these limits. But in practice, of course, in robotics, we care about a lot of things that are both discrete and continuous. So it's sort of, we understand how to do either by themselves, but we have often struggled to put them both into the coherent framework. Okay, we do it in task and motion planning as well as planning through contact. That's just two simple examples, important examples. Okay, even when you're doing collision-free motion planning, there's actually discrete decisions that get made. Do you go left or right around an obstacle? And then there's continuous decisions to be made about the particular smooth optimization over curves if you have velocity constraints and things like this. Okay, and you see that in our methods. You see things that are sort of fundamentally discrete, where we sample, we build roadmaps, and then we solve a discrete graph search problem, right? Or you see trajectory optimizations that can do wonderful things, but they struggle with local minima and other things we've talked about today. Okay, so graphs of convex sets is trying to being a coherent framework that brings both of these together. There's been ways, of course, to bring these together for a long time. With mixed integer optimization, for instance. And GCS is just a new way to write a mixed integer formulation that happens to make it incredibly fast to solve compared to most previous formulations. It came out in a handful of papers, led mostly by Tobia here, and I'll pull some examples here from his thesis, which I think is a really, really excellent introduction to the line of thinking that we've gone through. Okay, so what is a graph of convex sets? So imagine as a simple graph problem, a shortest path problem on a directed graph from a source S to a target T. We all know how to find shortest paths in that. You might think about doing it with A-star search or some other sort of incremental search methods. You might also know that you can solve that as a linear program. Okay. Graphs of convex sets are just a generalization on top of that, which is just maybe a conceptual framework of how would you write an optimization problem where you take your directed graph, but every time you visit a vertex on the graph, you're also picking one element out of a convex set. Okay, so you could think about it as jumping between islands or something instead of between vertices, but there's a continuous decision to be made every time you visit a vertex, and then there's still a discrete decision to get through the graph. Okay, and you're allowed to make continuous cost functions on the vertices, on the edges. Your cost functions can go to infinity, so you can have convex constraints on the edges or on the vertices. And what's important is that this turns out to be a nice sort of concept. We can transcribe a lot of interesting robotics problems into that sort of framework, and that we have pretty good solvers for solving them. Okay, so here's the linear programming, just a refresher if you haven't seen it recently. Here's the linear program for solving a shortest path on a graph. Okay, so if you take and make a discrete variable, a binary variable that's associated with every edge on the graph, and you say that the solution is going to be such that that binary variable is 1 if the edge is in the shortest path, 0 otherwise, and you have a edge weight on each of the edges, then a very simple optimization will solve this problem. Okay, so certainly the sum of the costs along the variables that are 1, that gives you the path length. Okay, you have flow constraints saying that basically at every vertex, the total flows going in or out must sum to either 1 or 0, effectively. Okay, but the sum of the flows coming in has to equal the sum of the flows going out. And then you'd like those to be integer variables. Okay, it turns out that if you do the binary relaxation of that, then in the particular case of shortest path, we know that the binary relaxation of that problem gives the optimal solutions. It's a special property. Okay, so the graphs of convex sets is just a slight generalization on that. Okay, so how do we write this down? Well, it's almost exactly the same, but now I have my cost length. My costs can be convex functions. Okay, and I'm also making this discrete variable decision of each vertex that I visit. Okay, this looks like maybe a bilinear objective function, so it looks a little bit messy, but this can be recast through a set of simple steps into a perfectly equivalent mixed integer convex formulation. Okay, and that mixed integer formulation basically uses a handful of the things that we think of as kind of the graph of convex sets machinery. Okay, the first thing is this transcription from the bilinear terms, things that you see of a variable that is always greater than 0, greater than or equal to 0, times some convex function. The use of, we use perspective functions to sort of write that as a convex function. Okay, and then there's something else that happens, which is, I guess, where maybe some of the magic is. So this would give you a convex relaxation. You can take a convex relaxation of that mixed integer problem, but those convex relaxations can be very loose, meaning that they're a poor representative of the original problem. And then what do you do in optimization if you want a tighter convex relaxation? There's basically one trick, which is you multiply constraints together. Okay, and then one of the important aspects of that, you guys have studied too, for instance, is trying to find what are the most effective constraints to multiply together. And in GCS, it turns out there's a particular set, the graph structure sort of highlights a particular set of constraints that you should multiply together. You can multiply, for instance, these flow constraints in the shortest path problem times the convex constraints of the sets. And these give you additional tightening constraints that make the convex relaxations tighter. But importantly, they don't significantly bump the complexity of the optimization problem. So if you started with a linear program, you still have a linear program after you've multiplied these constraints. Okay. Oftentimes, when you start multiplying constraints, you bump into a new complexity class. So we have a small number of constraints which multiply, which make the problem the convex relaxations of the problem a lot tighter. And if you've worked with branch and bound sort of methods for solving mixed integer problems, that means you can solve branch and bound very, very fast for big problems if you have tight relaxations. And in practice, for many of the problems we work on, we never even call branch and bound. We just solve the convex relaxation, and we can basically do a little bit of rounding to find the optimal solution. Okay, so that's sort of the crux of what GCS is a recipe for multiplying the right constraints to come up with very tight convex relaxations in problems whose problem structure is exposed on a graph. And it's not specific to shortest path. Okay, so just as another example, maybe you can write traveling salesman as an integer problem. It looks almost identical, actually. The path length is again sort of just the sum of the edges. Now your flow constraints are that you must enter and leave every vertex with a flow of 1. Okay, there's typically you'd have to do maybe some cycle elimination constraints too. I left those out for clarity here. Okay, and suddenly that small change makes this problem NP hard. That's interesting to think about why. Okay, but you can still take the same graph of convex sets machinery and now make a graph of convex sets generalization of TSP. People have studied this over the years. They talk about it as like TSP with neighborhoods or there's other names for it. So it's not a new problem in that sense, but the relaxations that we get out of GCS allow you to solve orders, like several orders of magnitude faster than the previously published results for TSB. Okay. And that's just two of a lot of different sort of graph optimization problems that one can write. So shortest path, traveling salesman, minimum spanning tree is another one. Here's sort of a GCS equivalent of a generalization of a minimum spanning tree problem, which you can solve on a graph. Bipartite matching, facility location. This is kind of a fun one to put this together in his thesis. And we all, he surprised us with it at the, I didn't even know he was working on it. And when I finally read his thesis draft. Okay, so imagine you want to make a sphere packing of the geometry of your robot. Let's say you've got a URDF of your OBJ specifying the robot, and you want to find the smallest volume sphere covering of the geometry of your robot to use in a fast collision detection. Okay, well, that's like a little combinatorial. You don't know how many spheres to be. You don't know if they should be on the left or the right. You can write that as a facility location problem. You can do the GCS extension, and then boom, you solve that now beautifully with the GCS machinery. Okay, so it's not just about motion planning. And you can do this thing that I kind of hoped for, which is you can do tabular plus linear model predictive control, right? So when you can write a finite MVP search, okay, if in the deterministic transition case, it's exactly the shortest path we already talked about. And the GCS transcription, importantly, when you do shrink the GCS regions to vertices, you get exactly the original LP. So we haven't made the problem worse by doing GCS, okay? But then on the other side, you can do the linear dynamics inside a GCS. To see that, if you think about just the LQR or linear MPC sort of problem, you can write that as a trivial serial chain in the graph. And again, if you write that down as a GCS and you do all the little optimizations we know about to reduce that optimization problem, then you can get actually exactly the same optimization problem you get out of your linear MPC in the two extremes. But then you can put them together and solve hybrid linear trajectory optimization. So that you call that a mixed logical dynamical system or piecewise affine. And you can now solve sort of the linear plus discrete version of MPC, for instance. Now this one, the convex relaxation, we haven't seen it always be tight, but it's still the tightest, so the strongest convex relaxation that I've ever experienced for that sort of, that's just a sort of empirical observation, is that we can solve these much faster than we solved with previous transcriptions. Okay, and then there's a couple examples we've done over the years to sort of think about this. And so if you want to now fly a quadrotor through a maze, okay, this is kind of a fun example because the people who are like graph theorists, they look at this and they think, well, that's a trivial problem. And I'm like, well, finding a path through the maze is a trivial problem, but finding like a continuous trajectory with derivative constraints that satisfies like the quadrotor, then suddenly that becomes a ridiculously hard problem, it feels like, right? But we can solve those jointly, and the GCS can find these things that are kind of these crazy trajectories through the maze, which is simple from the graph search, but we are simultaneously solving the continuous parts of it, and that's just the convex relaxation being tight. And previous mixed integer formulations wouldn't have been able to solve that at all. Too many binary variables. And different objective functions give you different paths through the graph. It's really jointly solving them in a way that we weren't before. Okay, so it's GCS for me is bigger than motion planning. In fact, I think motion planning is one of the harder ways to transcribe a robotics problem into GCS. But we have thought a lot about it. So I'll just give you a couple highlights maybe to wrap up about the trajectory optimization version of that, right? So I want you to think generally about what a convex set is, okay? So a box is a convex set, an ellipsoid is a convex set, but a convex optimization problem is also describes a convex set, right? In an implicit way, right? So the feasible set of a convex optimization problem. And so what we do in GCS trajectory optimization is each of those convex sets is actually a convex kinematic trajectory optimization problem, where the decision variables are the parameters of a Bezier curve and a scalar time scaling, okay? And then we use that and we transcribe a graph, which says that we're going to solve multiple kinematic trajectory optimizations problems, some of them that go left around the tree, some of them that go right around the tree, and we find a path that can find us all the way to the goal. This has led us to think a lot about SDP relaxations, like the ones that the perception folks are all working on here to try to do increasingly tight relaxations of the interesting trajectory optimization constraints. So we can solve quad rotors and minimum snap trajectories through mazes. Now, if the worlds are known, we can solve, I wouldn't call this task and motion planning. Maybe this is multimodal motion planning, where we have to pick up the order. You decide the order of picking up the mugs, whether to pick up the mugs. There's a little bit of that while simultaneously planning the continuous trajectories. We can make Spot do some fun things. Wow. Spot was doing cool things. And this one's also something about Spot. It's not going well. I'll put it up at the end if there's time. A little call out. So Bernhard's going to give a presentation on Friday at the main conference about how we've extended that to planning through contact, where the complementarity constraints, which are the force times cross distance constraints, which have been traditionally non-convex, have a nice semi-definite relaxation, and they can be used in the GCS framework. Okay, and we're trying to get more and more people to start hammering on this. We have GCS implemented in a mature way in Drake. We have GCS trajectory optimization and the supporting tools, and we're starting to see people use it. This is, wow, GCS is a lot better than BRM, but that's, he's trying to make me feel good. Okay, let me just end with one last idea. So for me, the reason I'm so excited about GCS is because it really has helped me make connections between a lot of the things I've learned about control over the years and some of the discrete graph search, okay? So we know how to do sort of stochastic or robust MPC in a GCS. We know how to do planning under uncertainty in a GCS. A lot of the things we know about designing controllers, there's sort of a GCS version of that. And to give maybe one example of that, people ask us what's the solve time on GCS, and it's pretty darn good. But if you want it even faster for like really fast multi-query, there's an interesting question of, can you do some pre-computation to make the GCS solves even faster? And we've been solving an optimization for every initial condition, but what if we solve a slightly bigger optimization offline, which solves for all initial conditions? And it turns out that the same way we think about, let's say, sums of squares, polynomial optimization for doing control design in nonlinear systems, you might write a value function and then write the conditions like you would do for approximate linear programming, dynamic programming. You'd push up on the value function from below as an optimization, and you try to find the tightest lower bound of your value function. Well, you can do that on a graph of convex sets, okay, and build a value function, let's say a quadratic form per set, push up on that, solve that once offline to compute this value function over the GCS. And then you can even do goal condition value functions. And then you do a little bit of look ahead online to overcome the gap between sort of an imperfect lower bound of the tractable but imperfect lower bound. And you use online look ahead to do this. And now we have like really fast, a little bit of pre-computation makes for really fast online playback of where basically there's no planning time anymore. It's constantly planning in the environment from new initial conditions to new final conditions. And it basically pre-computed the cost to go and makes that really fast. Okay, so graphs of convex sets is a way to jointly optimize combinatorial discrete structure and smooth continuous structure. It's giving us some of the strongest planners I've had. We often solve the global optimality. We can with the mixed integer, but even the convex relaxation often gives us global optimality. It's not really just a computational thing. For me, it's also become a conceptual framework. A lot of these problems fall naturally and it gives me a slightly different new sort of lens into looking at the problems I know and love. And I want to make sure I land that it's not just motion planning, although that is the one we've been pushing on hardest. Thank you very much. And there's, I would say now I'm trying to push people to the notes here as a source for all of the GCS papers we're trying to figure out and flesh out. Take any questions?
Thank you for the great talk. I was wondering, because you showed the sphere packing example, if you could use graphs of convex sets to do the decomposition of the space into convex sets that you need for motion planning. Is that something you looked into, or would that be feasible in reasonable time?
Yeah, that's a great question. So the thing that makes the decomposition of configuration space difficult is the non-convexity of the kinematics and the way that the geometry sort of works with that. So we've been trying to address that either with polynomial optimization or with nonlinear optimization for the initial pushing out. But we are trying to do more global versions of that, where we try to solve the discrete problems on, let's say, a PRM that's already been built, and you can sort of build out minimal sets of maximal cliques that cover the space. So it's connected, but at some point, in order to solve the non-convex optimization, we're making a leap, which was we're trying to bridge from the non-convex geometries into a discretized version of those. And at that point, somewhere on that boundary, I think you have to solve the harder version of the problem. Once you get discrete plus convex, then things are good again. Greg's there, yeah.
Great work, thanks. Do all of the convex sets have to be in the same dimensional space? They can all be all over so the graph also doesn't have to be embedded in any particular space. Okay.
You've mentioned a couple times relationships between this and the other like moment relaxations we saw in the previous ones. Is the GCS relaxation in some sense a special case of Lasserre relaxation, or is it something different?
Workout. Thank you. Sorry. So we did a lot of this work with Pablo Perillo, and so it's like the Perillo hierarchy and the Lasserre hierarchy kind of are the polynomial optimization. And Pablo, I think, would say that all of these are just examples of multiplying constraints together in order to make things tighter. And you can interpret the Lasserre hierarchy sort of that way. And if you're Pablo, you can interpret it that way easily. But so they're deeply connected. So that is one connection. We are explicitly using moment hierarchies or STP in order to push up in the lower bound function. So there's a very explicit, like each set can suddenly become something out of a SOS or a moment hierarchy. But I guess at the high level, really, it's more the philosophy of how to use strengthen your convex relaxations. Great question.
So last question, I guess, for me.
So once you formulate the problem as discrete plus convex, then if I freeze the discrete variables, then the problem is convex optimization. So why am I not satisfied with just finding the shortest path in the discrete graph and then just solving a single convex optimization? Do you observe that jointly solving discrete and continuous variables give you much better solutions than just finding a shortest path and then doing a single convex solve?
Yeah, so hey, thanks for raising that. Yeah, so absolutely, there are some problems where you could just solve a path first and then do the continuous and solve them separately, and you'd do well. Tobia wrote a paper with Stephen Boyd also called Fast Path Planning that was roughly exploring that version of it, right? Just to make sure that we had compared. But certainly for the harder planning problems, planning through contact kind of problems, we think that the solution you get by solving one and then the other is just absolutely not sufficient to solve the joint problem. Yeah. Thank you for asking that. Cool.
Okay, very last question, and then we will move on.
Thank you very much for this talk. What I was wondering is, once you have this GCS relaxation, that is, in a way, kind of a disjunctive programming problem, it's not fully convex yet, right? Because you might have some crazy nonlinear equality constraint somewhere. And once you have this relaxation, you have to solve a sequence of NLPs, I guess, right? No NLP, okay. So how do you solve something that doesn't have linear constraints, but is not a QP, but you have a GCS and you've got all these constraints together? How do you do you apply a second order method? Do you do some second Taylor expansion or something?
So we are currently solving GCS instances with Gurobi or Mosec or Clarabelle. I would love to get our Biral-Montero version working well, but we're in a very constrained setting. So I think there's additional work to understand how well Biral-Montero will work in those kind of settings. But there's no NLP being solved here. So we can, if we want to, at the rounding stage, add some nonlinear costs and constraints. We've done that. And we've done a lot of work on semi-definite relaxation, convex relaxations of the non-convex things. But what I would say is that given a non-convex problem, there's a couple things you can do. You can take a smooth convex relaxation like semi-definite relaxation, or you can, we have maybe you can sample, there's a couple things you can do, right? But we have one new thing, which is you can split with a disjunctive constraint, the non-convex optimization into pieces, right? And then leverage the GCS machinery or mixed integer machinery in general to sort of go in those cases. So any non-convex constraint could be handled this way. The ones that are relatively benign, I would say do the semi-definite relaxation, right? Do some rounding, and those will be fine. The ones that fundamentally change the path you should take, this is a way to sort of break that down and separate them out into a disjunctive. And the disjunctive is handled directly on the graph integer formulation, so you don't have any nonlinear disjunctive constraint programming. Thank you very much. Yep.
Thank you, Russ. You're fine. Yes, you're fine. Okay, so the last talk of this morning will be made by Armin Nurkanovic. So, sorry. So Armin is just obtained his PhD from Freiburg University in 2023, and he's now a postdoc in the still in the same team with Maurice Dill, and he will be talking about numerical methods for solving non-smooth optimal control problems.
So thank you for the introduction. I will just start with the outline and the switching here. Okay. Yeah. So as we noticed this morning, having some non-smoothness on combinatorial stuff, it's a hard optimal control problem. And I will start maybe with a warm-up to tell you all the algorithmic ingredients you need to have somewhat success at it. And one key thing is that it's often underestimated, I believe, is the time discretization. So if you use, I don't know, if you did trajectory optimization, who did use a few collocation or some Runge-Kutta method? So most of you. And if the problem is smooth, everything's fine. Nothing can go wrong, but just don't please use explicit Euler. But if it's non-smooth, there are some troubles. And I will show you a counterexample where this fundamentally breaks down. And then, of course, we have a solution to it, how to improve it. And then I will look in a particular class of non-smooth problems that we found to be useful for solving manipulation tasks. And to start off, I mean, non-smooth dynamics or hybrid systems, it's really a mess. In ODE smooth, you have linear and non-linear and you're done. But here, there's a lot of things and we want to have some order to know what's difficult. And this is also crucial in having success. And we like to classify them by their smoothness properties. And usually we start with what we call NSD1 systems. So it's a discontinuous or non-smooth right-hand side. And the first one is where you have a non-differentiable right-hand side, but still continuous. And examples if you have some absolute value or activation functions. So this is, I don't know, it's still Lipschitz. You have nice theoretical properties, but difficult for numerics. More interesting are what we call NSD2, where you have a jump in your vector field, hence a kink in your solution, like in friction problems. And these are a bit more difficult. And examples are piecewise smooth or piecewise affine systems, popular in control, or projectile dynamical systems, which I will talk today. And the last example, the most difficult one, mostly or better known by roboticists, is if you have state jumps, you have the phase plot of the bouncing ball. But it's basically if you have rigid body with friction and impact, you have also state jumps if you assume rigidity of your bodies. And if you do optimal control with these guys, it's really troublesome. So I will start with a general continuous time optimal control problem, and I will guide you through our philosophy when solving these problems. So I just here collected an objective. It's all in continuous time. So we look for some functions x and u, and I have some abstraction, a differential inclusion for all these NSD1, 3. There are many different systems, and some standard path constraints. And to solve these problems, to have success at them, you have to think all the steps through your solution. The first one is the reformulation. So will you pick NSD1, 3 to 3? Will you do integer or complementarity variables? This is still happening in continuous time. So you have to think how to start with your problem and where to formulate it. And then you need to pass, of course, we cannot really solve the previous problem on a computer. We discretize it in a way. So in the smooth case, everything is fine. But here, to get what people call today differentiable physics correctly, it's much more difficult, as I will show you. So we will need also some brain power to do so. And we can abstract, or maybe also one additional remark to the previous talk. This is here a direct approach. In indirect approaches, where you have Pointryagin, again, for most of these NSD 2, 3, 1, we don't really know how the Pointryagin conditions look like. And then we abstract this further away. If I pick complementarities, which are my usual choice, but we can do also integers, here's something that looks like an NLP, but we have this complementarity constraints. You know them maybe from the KKT conditions or from the contact problem. This will break down your standard NLP theory. So just don't apply directly SQP or anterior point method. You will need some more power to do this. And usually what we do is some relaxations. This is in an oversimplified way, solve a sequence of problems, but there are some other tricks to have success at it. So my main story is basically to have success, and I will hopefully convince you to the end, you have to think all the points. And I will now focus a bit on the time discretizations and show you one counterexample I really love. So we will start with a very simple problem, which has just a 2 minus sign on the right-hand side, so it's discontinuous. And the only degree of freedom is actually the initial value. And we have a path constraint minimizing the quadratic, and we have a terminal cost where we want a path cost, and a terminal cost where we want to reach a certain point. So this is some simple problem. We can solve it analytically and look that the quadratic objective is quadratic, but we can also discretize it. I took here the midpoint rule, because it has quadratic accuracy, and I would expect that it does an exact job. So I do this transcription from discontinuous to discrete time, and I take here 10 steps and look what the objective looks like, and it starts to behave quite wild. So I could decrease my step size and do it further and further. And what I see is basically the trajectories do converge, but the derivatives are completely wrong. Often they don't have even the right sign, and even worse, you get artificial local minima. And the fundamental reason behind this, explained in this very nice paper from almost 15 years ago, is that basically the trajectories converge if you discretize non-smooth systems, but the derivatives do not. So if you think of differentiable physics of non-smooth systems, it's not that straightforward. And you cannot really solve this by decreasing the step size. Another, let's say, obvious way to do this, what people do is just smooth it. I replace the signal with the tangent Simperboricus and decrease my parameter. And I look how the problem looks again with this setting. So I do a discrete time, sufficiently many steps, and everything looks fine for, let's say, a large sigma. But I have, of course, an error because I smoothed it. And some people achieve this by some randomized smoothing and things like that. So eventually you get something smoothed out. But if you use a standard, let's say, Runge-Kutta collocation method, and if you decrease your sigma, so your smoothing parameter, you will end up with a similar behavior. You will not be able to resolve this huge concentrated nonlinearity that happens at the discontinuity, and you will get, again, the non-smooth behavior and the local minima. So basically, very nonlinear is almost same as non-smooth in optimal control. So I will now propose a solution to this, because there are so many different systems of non-smooth systems. I will pick a particular example, and I take the projected dynamical system. It's conceptually very simple. So it's basically a standard ODE, a vector field. And if you end up at some constraint, which is here, the gray shaded here, you just project the vector field into the tangent cone such that you stay feasible. So, and this makes here a kink in your vector field, so that this makes the problem a bit non-smooth. But this is like a generalization of a standard ODE. So if you never reach a constraint, it's just an ODE. And for this guy, we want higher order accuracy, and also, more importantly, the correct sensitivities to avoid these artifacts. And before I do so, I want to first massage my equations a bit, because this projection operator, it's a bit like you cannot do easily computations with it. And so the projection operator is basically just an optimization problem with a quadratic objective and some set. And if you're inside the set, the point is the solution. And if you're outside, you get to the closest point. And what we'll do usually, we will have, like in nonlinear optimization, a finite representation with a set of inequality constraints. And if you have a constraint qualification, you may know from optimization, you can replace the tangent cone by the so-called linear feasible cone. So it's just a linearization of the active constraints, and you have something really algebraic to play with. And then we're using the KKT conditions of now it's also a convex problem, because this is convex polyhedral. You can reformulate this into something really algebraic. It's the dynamic complementarity system, and you have additional variable, a Lagrange multiplier. Important to note is that this is the only variable that is discontinuous, so this encodes through the complementarity all the hard stuff. The rest is continuous. You need really look close on these continuity properties when you design your discretization schemes, which I will do now. So a bit of a packed slide, but I will guide you through examples and the main ideas, the discretization, and I will do later the equations. So basically, in a standard discretization, the step sizes are fixed and you miss this discontinuity. And of course, here the shaded is the exact solution and the solid is the approximation. And if you miss discontinuities, you cannot really approximate well with continuous, smooth things, discontinuous things. And the main idea is to have the step sizes of the integrator as degrees of freedom. And then you have introducing equations to fix them, to get rid of these degrees of freedom. And what we do is so-called cost complementarity conditions. So usually you would just complement here these points, what would be your collocation stage points, for instance, everyone with the respective guy. But here inside a finite element, we complement everyone with everyone. And this will prevent switches to be inside the element or this integration step and force them on the boundary. And the last step is when you do this, you get the switch detection correct. But if you have no switches, the H's can be somewhat arbitrary. And you introduce additional constraints which will fix the grid if there are no switches. So it's like if you have no switches, it will just boil down to your usual Runge-Kutta or collocation. I will quickly rush through it, how it looks in equations. But it's basically on the left-hand side, I have just a Runge-Kutta scheme for this dynamic complementarity problem. So you may recognize the Butcher tableau entries A and B, and you take linear combinations of your velocity field, which I evaluate at respective points that I pick, and the algebraic part I evaluate also at the respective points. So just a standard Runge-Kutta or collocation, what you do in optimal control every day. And in the FESD, we just make these variables, introduce now more constraints, where we now notice here the difference in the index, everyone with everyone, to have the switch detection. And we take also the guys from before that has a bit of this deeper continuity properties, but it's just needed to make it work. And we have also some indicator functions defined by linear inequalities, which will basically remove or freeze this degrees of freedom in the step sizes. So this is basically the tricks you need to get a discretization that overcomes this zigzagging that we had in the example before. Okay, I will now head on to, let's say, the final or the practical. So this was all just preparing and telling the necessary ingredients and resolving some of the issues, but I want to also apply this. And so if we look again at this story of reformulation, time discretization, optimization, in practice, there are contact implicit optimization, where you start with the NSD tree, rigid body. So many people contributed, sorry for not citing everyone. And you would do a time stepping tailored to this rigid body dynamics, like an implicit or semi-implicit Euler, and you would maybe use IP-opt and solve a few, or SN-opt and solve a few of these problems. So this can work well, but you have to be aware of these wrong derivatives that can give you trouble. There's a way also to tailor the FSD for these problems to overcome this. But what I want to look today into is, again, now in the first part, in the modeling part, to use these projected dynamical systems to model manipulation problems and use the FSD as a discretization that I introduced a moment ago. So now we have FSD is the PDS is a first order system where we have, before we had the second order systems, so rigid bodies. So we have just position, and in the rigid bodies, we have position and velocity. And the key obvious insight is that you use these constraint functions as gap functions in your problem. And let's look maybe at one example. What's the difference doing first and second order systems? So first order systems on the left-hand side, you can only manipulate if you're really in the contact with the problem. Whereas on the right-hand side, the system has some inertia, so you can slightly push it and it will reach the goal. So, but by simplifying the system, you get for the same discretization of control intervals and integration steps, you get a much smaller problem, and hence you solve it much faster. So this is just to highlight a bit the qualitative differences when you make changes in your first step, but you gain something in computation. But this was relatively simple, and we usually want to model some more complicated shapes. And if we have shapes, I don't know, one way to do it, let's say we have some convex shapes, is to sample a few points and then look at the gap function between every point with every point. It's fairly inefficient. Another way is, as we love it all, is to solve an optimization problem. And this is a sign distance problem. I will guide you a bit through it. So basically, we'll take this constraint function in the PDS to be a solution of a convex problem, where we have basically the problem is parameterized by the state, so by the position orientation of these guys here, which is then two convex inequalities to represent the shapes. And then we have a scaling factor. And if the bodies are not in contact, we have to scale them up to bring them in contact, so our objective will be positive. Similarly, if they are already in contact, we don't have to scale down, we will have a 0. And on the other way around, if they're already penetrate, we have to scale them down, which gives us a truly sign distance function. Now, because this is a convex problem, KKT conditions are necessary and sufficient, we can use them and extract the C and the nabla C, which we need in our projective dynamical systems, combine all this together, adapt maybe a bit our discretizations, because the KKT conditions of the convex problem will introduce additional inequalities. Maybe you looked at sometimes at this sign distance functions if you rotate objects. So they have this sharp kinks, and this lead to non-smoothness that you also have to take care in the discretizations. And if you have more complex shapes, you will need, you can use a union. And Anton is also here, will have a poster on this, and you can look into more details. And I want to show some examples first with this PDS things, which converges really reliably. And we found very creative solutions. So they have to help each other to achieve some goals. And we don't give any special initial guess, it's just zeros. And it manages to find, following this pipeline, so here they have to really think hard to help each other. And there can be more complex scenarios where they really push things around to help each other. And this is just solving a few NLPs to get to this resolution. And we have a bit of more, with this convex optimization framework, a bit more complex shapes. Here, union of two ellipses. So they have to push around. The rotation has also to fit. So it really finds creative solutions. I like this a lot because it pushes around, and then to finish this, it uses its tail in a way. Also it can do spinning, breaks and makes contact when needed without any pre-specification. It's all encoded by the complementarity constraints. And also similar examples as in previous talk, T-shapes, so it's just a union of two polyhedral and the circles. You have two convex optimization problems for the sign distance functions, and it finds without any initial guesses cool solutions. And this brings me to the end of my talk. So one takeaway is if you want to solve non-smooth optimization problems, optimal control problems, don't think about the single good solver or the single good. You have to think about from the beginning, from the formulation, from the discretization and the solution, because they're all closely connected. And if you fail at one point, you probably get bad solutions. And today I covered reformulation where we looked at, should we use PDS or rigid bodies? So that's already the first step. And we looked at how use optimization to efficiently model sign distance functions. And I talked about time discretization, which is often a bit taken naively, I would say. And of course, everything we do is open source. So you're welcome to contribute and use it and try to reproduce. It's based on Casadi. So I guess a few people have used it here. And this brings me basically to the end. And because it was a very short talk, there's much more to it. So we had a summer school last September, and there's a lot of course material. And if you like, you can look into it. I think a few people from the audience are also in this picture. So I invite you to look at it and to contribute. And there are some references, and I'm happy to take your questions.
So one thing I wondered about with the time, whenever you're trying to find the sample times of collision, what happens if there's simultaneous collisions or multiple collisions that happened in the time interval? I couldn't tell if your complementarity constraints that you added captured that. Oh, sorry.
So the nice things, so sometimes like if it's infeasible, then it will be not fine. So the control will find solutions that are only like captured. So you will pick a, let's say, a control that will not read into this difficult solutions. Of course, it might be that they happen simultaneously at the right. So you can find such controls, but if it's something, let's say, infeasible, then the control will, you will not find a control that will do this. So if you have enough time steps, so it will, because they can adapt, if you have enough, so the number of time steps has to be greater than the number of collisions. So they will become very tiny and they will catch them.
Other questions? Oh, sorry.
That was pretty cool. So in the pushing example that you were showing, was there a consideration for the contact between the sort of blue, I think, triangle and the table as well? I guess I have a similar question where, what if I have contacts that are not well represented by LCPs? Or even like point contacts? Is your formulation able to handle stuff like this as well?
So if I understand it well, I mean, my short answer would be any distance that you can formulate as a convex optimization problems, which is any distance between convex shapes. A point is also a shape, a convex shape, right? Then you can represent it. Okay, I see. Yeah, we've been thinking about this. There's one in the references as well. So the trick with this sign distance function is that if you have a patch contact, you will find one single contact. Is this a bit a complicated story through where to place the normal and how the normal is, such that you get like a single point that has the equivalent as many of the points. So this sign distance formulation takes care of it if you compute the normals right. And it's a bit easier in the PDS. In the rigid body, it requires a bit of harder thinking. But in my references, so we thought about it. Long story short, you get one point that approximates a patch.
Thanks for the talk. And I think is it a must that we need to like a summation or sum all the HIs to equals to T? I think this constraint like break up the system's Markov property.
Look at the equations. So you basically, I mean, if you have a standard discretization, you have already a fixed step size and it adds up to T. And here you just add some flexibility on the H's. So, I mean, of course, you could also relax this constraint, but in principle, you can think of it, you have a fixed length of an interval that you decide before, what we usually do in optimal control, except it's a time optimal problem. And then you just see how you distribute it, where you sample with your discretization points. So this sum of T is needed to have a meaningful integration method, except you're doing time optimal problems. You can think of it as just as a control that wraps your time. You're flowing faster or slower just to get the switch at the point that you actually sample to make it work, to avoid zigzags. So if you have a pure simulation problem, it will be infeasible because then there is no solution that the switches as a fixed one that you pre-decide before. So simulations problem won't work. It's just, except at dumb block you hit the switches. In control problems, then the control will make sure that your switches are exactly at the points you have fixed. And actually we do this often because this removes one nonlinearity. You exploit the control a bit. Yeah, yes, it does, but you can really simply introduce a clock state, so integrator that sums it up, and then you have it.
Okay, thank you for the question, and thank you, Armin, for the nice presentation. So this talk is closing this morning session, so we can meet back at 2 p.m. So thank you.